Okay, so it's about time, but before we continue with the presentation, are there any questions that we should discuss at the moment? I see that there are some questions about MPI run was unable to launch the specified application as it could not access or execute an executable. This is most likely caused by either there was a problem when you compiled aspect in the plugin directory. So make sure that there is an aspect in the plugin directory, or you are inside a different directory and the plugin directory is not actually a subdirectory of the directory you are currently in. In other words, you are not currently in the session-2 directory when you execute that command. If you try the commands that I put in on the break slide, so the commands at the bottom of the slide that is currently up, the run free surface model part, then it should work, because that one does not rely on the fact that you are in the session-2 directory, and they don't rely on the fact that there is an aspect in the plugin directory. Okay, it seems like there are still some problems. Maybe we can discuss them in the discussion session after the presentation today. It's not absolutely crucial that you run it, because I will show the results on the screens as well. We should try to make this work for the models that we are going to run tomorrow, but today should be fine. Okay, so then let's check what the model actually produced. So when I switch over to my virtual machine, I see that the model has finished in a bit less than 3 minutes for my model with the 6 processors. It might have taken a bit longer for you, or it might even still be running. That's okay. You don't need to follow along at the moment, but if you want, you are welcome to. So first of all, let's check with ls the contents of this folder. There's now a new output directory that is called output-free surface with crust. So let's go into that directory. And as a reminder, in the Linux terminal, you can always auto-complete a path or a directory if you press the tab key. So if you already put in some letters and press tab, then it will try to complete the path. This saves a lot of time while typing path names. Inside this directory, there is again a solution.pvd. So let's start power view with the solution.pvd as an argument. And the model looks more or less the same as the one that we ran earlier. And if we look for the temperature, then we will see the same spherical temperature anomaly. But if we switch the presentation to the viscosity in this selection in the top, then you will see that now we have a low viscosity mantle, viscosity of 10 to the 20, below a high viscosity crust with a viscosity of 10 to the 23. Now, the point of this model is not really to discuss whether these numbers are correct, but just to show that we used this plugin that modified the material model to set different viscosity in the top layer than it did in the bottom layer. And I'll close this area for now because we don't need it anymore. If we take a look at the output of this model run, you will see that for every time step, you also have a new line in this output compared to the model that you ran yesterday, which is the minimum and the maximum topography. And this is what was computed by the topography post-processor that we selected in the parameter file. And these values are also added to the statistics file that we discussed yesterday. So let's plot them over time, just like we did with the average heat flux yesterday. So we are still in the output free surface with crust directory. And I will again use the GNU plot program that we used yesterday. That's GNU plot. And the command to plot this topography is plot statistics. So the statistics file using the columns 2, which is the time, and the topography. And I looked this up, so you can look up the number in the statistics file, but it should be the same as for me, and that is column number 15. So using 2:15. And this will show you the development of the topography over time, the maximum topography. So the maximum upward movement of the surface above the rising sphere. And you can see how the topography increases and then decreases as the sphere diffuses below the crust. So this is what we expected. Now, the last thing that I want to do today is to show you how to make a small change in the plugin and to recompile the plugin and then rerun the model and take a look at how the results change. We will probably not get to the part where we actually compare the results, but that is something that you can do for yourself once the model is finished. So let's exit GNUplot for now by typing quit, enter. And let's go to the plugin directory. First, let's move out of the output directory and then into the plugin directory. And let's reopen the simpler with crust.cc. So again, I'll use the code editor because it already highlights the colors of the code. I will scroll down to the evaluate function that we looked at before. And let's say that we not only want to change the viscosity in the upper layer, but we also want to change the density in that layer, which makes sense. The crust usually has a different density than the underlying mantle. So for that, we would want to change this part. We want to not only change the viscosities, but we also want to change the densities. Now, if you are familiar with C or C++ in programming, then what I'll do right now will look completely trivial to you. If you are not familiar with C and C++, then it might look completely confusing, and it's a bit hard for me to explain everything on a level that's interesting for you. So I will do what I want to do and explain the basics about that afterwards. And if you didn't follow along, then feel free to come to the discussion round after the lesson today, and we'll talk a bit about C and C++. So first of all, we need to add some parentheses around these statements because we want to add a second statement, and we can only disregard these parentheses if we only have a single statement in the ifs. Next, we want to move this line that defines the density into this else part and into the part for the crustal layer. So if you think about it, so far we have done no change at all. We still define the density exactly the same as before. We just moved it in a different place in the code. So if we are in the crust, it will now be defined exactly as before. And if we are not in the crust, then it will also be defined exactly as before. But now let's say we change the reference density in the crust to a fixed value. Now, this is not good coding practice. We would want to make this a parameter that can be changed in the input file. And I'll leave that for you as an exercise. It's a very simple, or well, let's say it's a reasonably simple change because you can just look at what happens to reference density and the reference density parameter and repeat that for an additional parameter that you name, for example, crustal density. But for now, let's just put in a hard-coded number of, let's say, 2,700 cubic kilogram per square meters in this case. And then we will save this file by using File, Save. No matter which editor you use, there's likely a File Save option in the menu. And let's close this window again. Now that we have changed the source code file, we also need to recompile this plugin. If you remember the first time, we had to run the cmake command and then the make command afterwards. Because the cmake command only creates information about how to compile this plugin and nothing about that has changed, we don't need to rerun the cmake command. So it is enough to just rerun the make command, which will recompile this plugin, which will take half a minute or so. Afterwards, we can move one directory up into the directory that contains the parameter file. And we will take a look into the parameter file. And we will make one simple change. So now that we changed the plugin, this file is actually different. But we want to keep the output of the directory of the model that we had run before. So what we'll do is we'll select a different output directory to avoid overwriting the output that we already have. So we'll change the output directory to a different name. For example, output free surface with density jump. And I'll also save this file. And then I will rerun this aspect model. And in case you didn't follow along with the code changes, I will start this model and then I'll go back to the code and show the changes again that I did. So I start this model. Actually, let me start it with 6 processors like I did before. And then I switch to the other window and show the code changes again. So this is the state of the simpler with crust evaluate function right now. And the highlighted lines are the lines that I changed. And while this is running, I'll take a quick look into the chat. Okay. Seems like there are a few questions that we will have to discuss after the presentation. There's an interesting question if you have to worry about naming conflicts with other aspect plugins. So let's say you want to not use the 2700 that I hard-coded, but instead you want to use a variable called crustal density. And the simple answer is you don't have to worry about naming conflicts, because everything we do here is inside the simpler with crust class. You cannot conflict with names that are defined in other aspect plugins. They are completely encapsulated, is the word you would use. But they are essentially independent from each other. Okay. So I'll close the chat. I'll close the code window. The model has nearly finished, and the only step left that I wanted to do today is to show you the difference in the output between the model that we ran before, the one where only the viscosity of the crust was higher, and the model that we changed, that we ran right now, where the viscosity was still higher, but we also reduced the density in the crust. And I will show you the difference again using the GNU-plot program. If you want to follow along in this part, make sure that you are inside the session 2 directory and not inside one of the output directories or the plugin directory. So you want to be in the session 2 directory so that you can type in the same command that I'm typing in. So I'll go into GNU-plot, and then I will use the plot command. And this time I cannot just type statistics because I'm not in the correct directory. I want to type in first the output free surface with crust/statistics using 2.15. So this command would give exactly the same figure as before. We just have to put in a different file path because we are now in a different directory. But we also want to plot the other file. So we will add a comma space and then the path to the next file we want to plot. So that's output dash free surface with density jump slash statistics using 2:15. So what we will do here is we will plot the two different statistics files, one with only the viscosity difference, one with the viscosity and the density difference, and we will see how they compare. And if I didn't put in any typos, then this will hopefully work. Let me maximize this window for you for a second, just so that you can see that this is actually one line. So plot output free. Ah, there's the first typo. Free surface with crust statistics using 2:15 and output free surface with density jump / statistics using 2:15. And then you will see that these two lines differ. The pink color or the purple color shows the original free surface with crust, and the teal color shows the free surface with density jump. And you can see that the topography is larger in the model with the density jump because the crustal layer poses less of resistance against the topography. Or in other words, the same force can lift this crust a larger distance because it has a lower density. And this is about everything I wanted to say today. If there are any questions, then I'm happy to take them. And otherwise, we'll go into a quick introduction into lithospheric modeling by John in a minute. What is happening at the end? Yeah, I expected that question. Okay, so everyone who wondered what happened at the end of the teal question gets bonus points for being attentive. If you take a look at the paraview output of that model, you will see that the stabilization of our model actually breaks down at that point. You will see that the free surface starts oscillating. So in this case, we would need to either restrict the time step length, or we would need to increase the stabilization parameter for the free surface in the parameter file that we discussed before. And this shows you also an important point about these free surface models, that you need to consider the properties of your model. So it's not enough to tweak these parameters once. You will have to think about what kind of model you are running, and not every model is stable with the same parameters. So reducing the density actually increased the tendency to create oscillations of the free surface for this model. Which is also why the other ways to model free surface, like the sticky air layer, are still very good approaches, even though they feel less intuitive than just modifying the mesh, as in this model. Okay. If there are no more questions at this point, then thanks everyone for the attention, and I will hand over to John to give a quick theoretical introduction in what we will be doing tomorrow and the days after.
Yeah, so
okay.
Around how much time do we have? How much time do we have? Maybe
20 minutes left for today.
Okay, sounds good. We'll see how far we get. I'm actually going to start with one of the simpler examples, and then we can just see how far we get into that.
Yep.
All right. All right, can everyone see the screen? Rene, is this viewable for everyone?
Yes, this is viewable.
Great. So then, just for context, a quick sort of overview of where we are in the tutorial. So then now we've already gone through the introduction to the aspect basics and sort of basic modifying and coding an aspect. And now we're sort of getting into the more complicated things. So now we're going to have, Anne and I are going to give an overview of lithospheric deformation. And then in session 4 on Thursday, we'll move into two-phase flow with Juliana. And then on the last day, Menno is going to it's going to cover complex model design with the geodynamic world builder. So with lithospheric deformation, we sort of subdivided into multiple different components to sort of just make things a bit more clear and sort of subdivide, clearly discrete topics. And what we're going to do today is, rather than jump immediately into an overview of the nonlinear components of lithospheric deformation, I thought it'd actually be easier to start with a linear rheology example, in this case, viscoelasticity. And we're going to go over sort of the basics of viscoelasticity and then an example with a viscoelastic bending beam. And we'll see how far we get with the example. We may need to pick that up tomorrow as well. So, some things to note before we start on lithospheric deformation. This is just sort of an FYI on a whole bunch of different topics. So then the first thing to note is that there are a huge number of contributors to like the underlying source code and benchmarks and cookbooks associated with lithospheric dynamics. This includes basically all of the maintainers and developers of Aspect, and then many more contributors. So what Anne and I are going to present today is certainly not just our work, but it represents the work of many people over basically the entire existence of Aspect, probably all the way back to the beginning of when Timo, Wolfgang, and others started writing it. So, second point, computational lithospheric dynamics, it's a vast topic. I've been working on these kind of problems for 10 years, and I'm still constantly learning about new things. And this tutorial, as such, is meant as an introduction rather than a comprehensive overview. There is no way, even over the course of 2 weeks, we could give you a comprehensive overview of everything associated with this topic. So think of this as just an introduction, as sort of like a gateway to learning how to do these more complicated models. And so then after this component is over, the next step would actually be, rather than to jump into your own modeling, if you're new to this kind of sort of types of models, would be to start looking in aspect of additional cookbooks and benchmarks. We're only going to cover some of them, and there's a lot more. And so then absolutely the first step is then to just keep going through the existing examples until you have a better intuition for how these things work. The next step would be to start going through the Aspect source code. And then, especially before you start on a very specific modeling topic, start reviewing the literature. And what you're going to find is that, between different codes and different groups, some people do things in a similar fashion, but in some cases people do things differently. And it's a good starting point to know what has worked or not worked in the past, because for some problems, it turns out some methods work and some methods don't work. And we're constantly learning and adapting Aspect, according to that. The third thing is we're going to repeat certain topics throughout the tutorial. So I'm going to cover the introduction tomorrow to how nonlinear viscous flow and plasticity work, but Anne's going to go over that again. And that's basically because this is such a complicated topic. It's probably not going to sink in the first time, especially if this is the first time you've looked at these things. So then we're absolutely going to repeat things, and that's very intentional to make sure they sink in. So the last and possibly the most important part is that, and I'm sure all of you probably realize this already, is nonlinear computational modeling. It's really hard. And so then, even though we're going to give you these examples, which sort of do fairly complicated problems, if you're going to do a novel study on your own, it's important to properly set your expectations for the time required to do a new investigation. And so then maybe if you're doing a study which builds directly on one of the examples we give you, it might not take a couple years, but in most cases, whenever you're starting on a new project with nonlinear lithospheric rheology or whole mantle convection, it takes a year or two to sort of get into these things. And simply because with the nonlinear rheology, all sorts of different issues arise, and you often need to implement new numerical methods or new physics to address your problem. So it's good to properly set your expectations at the beginning, even though we're giving you examples which are quite realistic in nature. So as the first part, if we're going to go into linear viscoelasticity, the first thing to do would be to go back to your virtual machine and open up a new terminal. And what you're going to do is you're going to CD into the Aspect tutorials, then 2020 Tectonics modeling tutorial, and then day 3. And so then I'll open up my virtual machine in just 1 second and go into that. But then But then what you can do is actually open the bending beam benchmark, and it'll just be easiest to show you that. So I quickly go to my virtual machine. Oops. Oops. Yes. Just going to quickly increase the size of this. I'm at the maximum. Okay, so I'm in the main folder. So what I'm going to do is I'm going to CD into the Aspect tutorials. Then CD into the 2020 Tectonics modeling tutorial. And then CD into day 3. And there are a bunch of examples in here. And the first one we're going to run is the viscoelastic bending beam. So what we can do quickly is if we want to use LeafPad to open this. Sorry, then we increase the size of this.
Yeah, so John, we only see your PowerPoint. If you want to show anything else, you only shared the PowerPoint window.
Sorry. Oh, sorry about that. I didn't switch that over. How about now? Can you see my virtual machine now?
Yes.
Great. So I'll go back and redo those commands actually. Sorry, give me 1 second. It's actually not letting me modify. It's actually not letting me enter my virtual machine as I'm doing this. Sorry about that. Just give me 1 second. I had to restart quickly.
Yeah, let me just mention that probably in the Aspect tutorial folders that you get cloned, it's called session 3 and not day 3. Just so that people know where to go.
Oh, did it get modified to session 3?
Yes, I modified it after you put your files in, sorry.
Okay, you know what? So what I'm actually gonna do is we can run the viscoelastic. I will modify my slides and we'll actually run the example tomorrow. But what I'll start doing is I'll start going through the example, the parameter file, and then we can run it tomorrow just for simplicity. All right, so let me go back to the PowerPoint. Sorry about that, everyone. So the example we will run tomorrow will be the viscoelastic bending beam. And if you want to run that today, you'll need to change this command from day 3 to session 3. But then the command would be the same. You can just point to your aspect binary, either the debug or the release one. Use however many processors you want. And right now in the parameter file, the end time is set to 10,000 years, but if you can, but if you have half an hour to run it rather than 15 minutes, you could change it to 50,000 years, which is the standard sort of end time for this benchmark. So some things to note before we get started on, oh, sorry, we already went through that. And then, yes, so viscoelasticity, why is it important? So then the lithosphere, it undergoes deformation through a combination of various mechanisms. This includes viscous flow, plasticity, which is basically brittle failure, or our approximation for brittle failure, and elastic deformation. And so why is elastic deformation important and where is it important? It turns out in regions undergoing flexure, elasticity is a large contributor to the overall deformation. So this could be in basically the hinge zone of a bending subducting plate, or can be under, say, oceanic lithosphere, which is undergoing flexure due to, let's say, formation of volcanoes like the Hawaiian island chain, which is bending it down. So viscoelasticity is extremely important in these regions. Thanks. So then, what's exactly the numerical procedure for looking at viscoelasticity, and how do we add this to the governing equations? So then it turns out, right, our aspect was formulated originally for viscous flow. So it was inherently designed to do elastic problems. There are other codes, for example, like Abacus, which is a commercial code, or codes like Flock, which are specifically designed to handle elastic problems and then actually modified then in other ways to do the viscous problem. But we're starting out from the other side. We're starting out with viscous governing equations, and then we're basically adding elasticity on top of that. So how's that done? It turns out basically everyone in lithospheric dynamics who starts with the viscous approach uses the methodology outlined by Lou Marazzi from a paper in 2003. And this is basically the formulation put into his cold underworld. And although different codes, there are some slight tweaks between how this is done. Basically, all the codes follow the same general approach. And the approach is this. Once you've calculated a viscosity related to viscous flow, this could be a fixed linear viscosity, so let's say 10 to the 24, or it could be a viscosity derived from diffusion and dislocation creep. Is you take that value, so this reference viscosity value here, and you calculate what's known as a viscoelastic viscosity value. And what the other terms are in addition to this viscosity value here are basically this elastic time scale. In most cases, that's basically your advection time scale you're using in your models, but if you can also relate this to things like relaxation time scale. So often the times we're putting into here would be 1,000 years or 10,000 years. And then also the viscoelastic shear modulus, which is in units of stress. And so then once you've used these terms to calculate your effective viscoelastic viscosity or a modified viscosity, is then you need to think about how you calculate accumulation of viscous stresses over time. And so then what this equation right here is saying the stress associated with viscoelasticity at the next time step, at the point in the future, or at the current time, you can say is equal to the viscoelastic viscosity times all of these terms in here. And these terms are the deviatoric strain rate at the current model time, then plus the old stress from the previous time step divided by the shear modulus, and then this elastic time scale again. And then here, these terms are, again, it's the old stress, and W is this, and then W is the spin tensor. It's basically related to sort of the vorticity. I mean, it's very similar to the vorticity tensor, or it is exactly the vorticity tensor. I can't remember exactly. But then you're dividing this by the shear modulus, or the shear modulus again. And so then once you've done this calculation right here, then you have the stress at the current time. And what you then do at each time step is then, this is basically the heart of how you're adding viscoelasticity into the governing equations, is you calculate a force associated with these stresses. So what we're saying here is we're taking the viscoelastic viscosity divided by the shear modulus, multiply it times the elastic time step, this value down here, and then multiply this entire term by the stress. And this basically gives you a viscoelastic force. Then what you do is you add this term to the right-hand side of the force balance equation. And this is one of the two Stokes equations. And then you basically have viscoelasticity in your model. It's actually, once you sort of know the procedure, it's actually not that bad to do. And then as deformation occurs and things are moving over time, you need to track this stress tensor with either compositional fields or with particles. Right now, we only have that feature, the tracking of viscoelastic stresses implemented with compositional fields, but soon it'll be also implemented for particles as well. So that's the general procedure. And we can go into the details of that later. So then, the viscoelastic beam, and we'll actually run this example tomorrow, but just to give you a brief overview of it, is so then this is sort of a classic example of what happens if you have a plate undergoing flexure due to gravity, and then when you turn off gravity, then as viscoelastic stresses accumulate, if you remove that driving force, the beam should actually rebound and return to its original state. So what does this model look like? What we have is we have a light viscous fluid basically surrounding a dense viscoelastic beam. So then the blue fluid is basically deforming only in a viscous fashion and has a lower density in this beam. And then this beam, it has a higher viscosity, it has a lower shear modulus. On this side of the model, there's no slip. On the top, bottom, and right, it's free slip. The model is 7.5 by 5 kilometers. There's 100-meter grid spacing. And the only thing driving deformation is gravity. So what happens when you turn gravity on, the beam is denser than the fluid, and it's going to bend. And the flexural profile should exactly match the parameters described by basically the shear modulus and its bulk viscosity. And so what happens is when we run this model, so this is sort of enmeshing showing deformation through time, you can see the beams undergoing viscoelastic flexure. The colors being shown here are actually the compositional fields. So in this case, the value is 1 initially, and this represents the beam, and it's 0 in this region because that represents the background fluid. And so what you can see happening over time, the beam is bending, and the flexural profile, again, it's a reflection of its bulk viscosity and the shear modulus. But you also see whenever you are vecting compositional fields, you do see some diffusion. And so you can see at the edges, there's starting to be some diffusion around here. It's not an exact line. So then, the other important thing to notice is that after the beam has undergone deformation, is you're not just accruing in a variation in the viscosity profile, but you're also accumulating viscoelastic stresses over time. So what we're plotting here is the horizontal stress components of the stress tensor. And what you can see it's basically a mirror reflection of itself. In the top, it's high, you have positive stresses. In the bottom where it's bending, you have the negative value of that stresses. And it's sort of roughly matching the flexural profile of the beam. Now you'll note some sort of these anomalies down here. That's related to sort of weird averaging things going on where the beam is no longer perfectly well defined due to the diffusion of the compositional fields. Using particles will actually probably help smooth some of that out, but then this is sort of a common feature you see. And that you might see some anomalies at the edges of very sharp features if there's been some diffusion. But the key point here is after 50,000 years, you've had accumulation of viscoelastic stresses. So now, let's see how much time we have. What do you think, Rene? Maybe 10 more minutes or 5 or 10 more minutes?
Well, I think originally we said we would stop more or less on the hour, which is in 2 minutes. But if there's no good point to stop within the next 5 minutes, then sure, I guess nobody will.
Well, how about what we can do? How about what we can do is I actually just go to the end of the model result, and then I'll go through the parameter file tomorrow.
Exactly, everyone. It's probably better anyway, because then we will go over the parameter file right before we run it.
Exactly. So then what this is showing is the beam underwent initial deformation with gravity on for 50,000 years. And what it's showing right here is if you turn gravity off, then the beam rebounds. And so you no longer have the driving force pushing that beam down, but you still have the accumulated stresses, which accumulated during the bending deformation. So what happens is you turn gravity off, and those elastic forces which have accumulated are actually pushing the beam to restore its initial shape. Now then, I only ran this for 300,000 years, so it's not entirely done rebounding and the stress is relaxing, but if you ran it for 5,000, if you ran it until 500,000 years, basically it would be almost entirely at its original position. And you can sort of look at that in terms of the stresses. So what you see here is those stresses which had accumulated to values of around 200 megapascals after 50,000 years is over time, they're slowly decreasing. And once they go down to a value of 0, then effectively you should have retained your initial position. Yep, so then I think that's a good point to stop for today. And then we can go through running the example tomorrow after we've modified the, the location in the folders and whatnot.
Okay, that sounds good. So just as a reminder, so we will probably do this today, just like we did yesterday. That worked quite well. We will take a short break now, maybe another 10 minutes or so. And everyone who still has questions, either about the first part, about compiling aspect, about compiling plugins, about the free surface, or about the last part, about the introduction to viscoelasticity, feel free to stick around. If we will mostly discuss specific questions. So if you don't feel like you have a specific question at this point, then there's no benefit of sticking around really. And then we'll discuss for at most an hour or so the questions. and we will reconvene tomorrow at around the same time we did today and yesterday. So please be back in 10 minutes if you have something that you want to ask us. And otherwise, we'll see you all tomorrow morning. So yeah, thank you for today and see you tomorrow.